let's just kind of get a feel for where we are in the course. So we have covered a little bit about processes already in the first exercise in week 3 lectures. So here are the things we learned. We learned that functions don't actually do anything. The things that does something is the thread. So if you want to do more things at the same time, you don't write more functions, you make more threads. We also learned, or at least experienced, that a program can consist of several tasks. Like a program doesn't just do one thing and produce one output, it often produces several outputs that are at least largely independent. So if they're largely independent, it makes sense to program this as a bunch of threads that do independent things and have independent areas of responsibilities and not just one giant thread that does a lot of things that interact. We also learned, and this should be fairly obvious, but cybernetics, a task has inputs and outputs. So a task needs something in order to do what it needs to do, and it does something. It produces something into the output, into the outside world. So if you have multiple things to do, it makes sense to, that's why it makes sense to separate it into multiple tasks, because, well, doing multiple things from one place instead of doing multiple things from multiple places is actually more complicated in terms of code. But of course, if you need the same thing multiple places, then you need to start communicating and so on. So this is where the interactions come into play. Like one task might depend on the results from a different task. There are 2 main ways to do this, of course. We talked about shared variables as a way of interacting, and we talked about message passing as a way of interacting. And we're going to compare those a bit more in detail again today, because it's worth repeating. But we also learned that the fewer interactions we have between tasks, the better it is. Because if you have a lot of interactions, you have a lot of things to keep track of at the same time. And our goal is to program robust software. And the fewer things we need to keep track of at one time, the easier it is to kind of focus our attention on making the one thing that we're making right, instead of making the one thing out of a lot of things. Like if we're able to isolate, so we can focus our concentration on one thing at a time, it's easier to program. That's it. That's all there is to it. So don't try to be overly clever and do a lot of things at once, because you're going to make code that you don't understand in a week from now. And that's, sometimes fun to be like, oh, I made something really complicated, and then you come back later and you go, who made this? I was a different person back then. So we've also learned a little bit about fault tolerance and failures and crashing and miscommunication, and well, we know we're making robust software. So we know that failure is not just that it's not an option and we're supposed to make stuff that doesn't fail. We know that things will fail and we need to be able to deal with it. So the way we deal with it is with redundancy. We separate our thing into lots of small things, and as long as at least a couple of them work, you don't need everything to work at the same time. We just need some of it to work. So if you have a single failure, it won't collapse the entire system. That's the goal. And we know that the failures can come from 3 major places. You can argue that this is a learn by heart list, but it's fairly obvious. So we get the wrong results, we aren't able to communicate, or the thing that we stored was some data that we weren't able to restore. And we handle all of these with redundancy. So we do more in more places. We send more so that lost messages are dealt with in some way. And then we store more, so we store duplicates. And you're going to do this on the elevator project, of course, right? So you have multiple elevators, that lets you do more. You have communication between them, it's up to you to do the communication right. We're going to talk about that when we talk about distributed systems, but the thing that you need to do there is you need to send more. If you send something once and it gets lost, then you need to send it again. And of course, you're storing more. Right, so you have all of the orders. In case an elevator goes down, you need to be able to do that work somewhere else. So you need to store that work somewhere else as well. So again, I think this is fairly intuitive. Like the moment you think about how would you solve this problem, you go, okay, these are all the things that you need to do. Oh, I didn't start the recording of Blackboard. I'll upload it to YouTube then. Cool. And we also, again, we haven't really covered this in great detail yet, but we will when it comes to, when we talk about distributed systems. But again, let's get the intuition in place. We need some kind of negotiation here. Like if we're doing more, we don't want necessarily everybody to do the same thing. If we're sending more, like maybe only one of the messages is the correct message. If we're storing more and they disagree, which one of them is the correct version. So we might require some amount of negotiation there to figure out what is the valid thing of the things. And that could be a hard problem to solve, and it could be an easy problem to solve. Sometimes it's just which one is valid. They're both valid because we don't know, so we're just going to take all of them. So again, for the elevator system, you lost connection to an elevator, and they disagree about who has what orders, and you go, well, I'm just going to take them all because it's better to do too many than to do too few. But if you have like an airplane ticketing system and you're like, oh, this one ordered that seat and that one ordered a seat. Oh, what's the best thing to do? They can share the seat. It's not a valid solution. So, or if you have a bank that's like, oh, they can share the money and we can just duplicate it, it's not a valid solution. So it really depends on the situation. Let's do some recap on the exercise front. On the first exercise, the last engineering question was, which one do you prefer, message passing or shared variables? And well, the question wasn't which one is best, the question was which one do you prefer? And of course, creating or using the thing that everybody prefers, you can make a solid argument that that's the best thing to do, because doing something that you like best but everybody disagrees with you might not be a great choice. But that's not exactly a scientific point of view, because it's, the truth isn't determined by consensus, of course. But there is some validity to considering consensus. So the question was, what do you think is best? And what was the answer? Well, the overwhelming majority of you answered message passing. It's not even like 90-10, it's like 95-5 or even higher. And that's somewhat surprising, considering that almost all of you also used more time programming the message passing parts. Now, some of this, of course, is the result of that being in a new language, and you need to learn the new language. And some of that is also because it's completely new and you, to some degree, also overcomplicate it. But still, despite this, you preferred message passing. And the question is, well, why is that exactly? And I'm going to list up some reasons why I think that is the case, and you'll have to agree or disagree. And if you do disagree, come out with some ideas as well to see if we can figure out why it is. But here are the two main reasons that I could come up with. The first one is on the interaction front. And this is like the foundation for code quality. There are three things that are interacting in shared variables way of thinking. You have the threads, they're interacting with each other. You have the variables, the threads are interacting with the variables. The variables are interacting with the locks, because if you use a lock but don't use a variable, or use a variable and don't use a lock, then the program doesn't work. And of course, the threads need to actually lock the locks. So you have like a triangle of interactions here. And that's literally, as by the definition of the word, this is literally complex. These things are all interleaved. They're interwoven. You can't use the variable without using the lock, and using the lock without using the variable is meaningless. The problem here is that all of these interactions exist implicitly. So there's nothing in code that says that you can't use the variable without locking it. There is, for example, in Rust, you can do this. So the variable is owned by the mutex. So you can't use the variable without locking the mutex, and if you lock the mutex, you will get the variable. But it doesn't change the other interaction, which is that you have multiple threads interacting with a possibly even globally shared variable, which means that anybody could use it at any time, at any place, and you don't really have any control of it. But with message passing, all of these interactions are explicit. So in order to get a variable, it needs to come from a channel. In order for it to come from a channel, it needs to be sent by another thread. And in order to send the variable, it needs to be received by another thread. So in order to use the variables, You need to use the channels. In order to use the channels, you need to interact with the threads. And you know, at least in code, you know who's on the other end, because the channel, at least by convention, but you will only have a sender and a receiver and not multiple, usually. And that just makes things easier to keep track of. So again, it's just fewer interactions and more explicit interactions makes it easier to keep track of. The easier it is to keep track of, the easier it is to write good code. And the other side of it is in terms of things like ownership and responsibility. You can't have ownership if you aren't responsible for the data. And you can't be responsible for something that you can't have ownership over. Because if you're responsible for it and you have shared ownership, you have shared responsibility. And shared responsibility is just like, well, who's in charge anyway? So this is also just a way to limit our scope of attention. If we are concerned with everybody else all the time, then it's hard to write the code in a single thread because we need to worry about everyone else. So these seem like the reasons why people prefer message passing. Do we have anything else to add to this? Any more ideas? Maybe they will appear later, maybe not. But this seems to be, as far as I can tell, the root cause. Now there are some constraints to get these message passing benefits. We need to enforce a couple of conventions. One of those conventions is the server way of thinking. In order to get the unique ownership, you need somebody to be uniquely responsible. That's what the server is. Now you can think of this as a class in object-oriented programming. It contains a for select loop and it has local variables. So unlike a class, it actually does something. Classes don't do anything, they're just containers. And you can think of the channels into that server as the member functions of that server. And a couple groups picked up on this kind of similarity between a message passing program, a process-oriented program, and an object-oriented program. But the key differences are that, again, the servers actually do something, and because they do something, they can actually have that responsibility because they're actually, they can actually have the ownership, and because they have responsibility because they can do something. Because if you're not doing anything, you can't be responsible for the changes because you're not changing it. And the other difference is that when you have channels as parameters, whoever is on the other side of the channel doesn't need to be exposed to all of the channels. They're only exposed to the one that they're using. We're going to get back to, in much more detail, exactly the differences between a process-oriented and an object-oriented program later on when we talk about testability in a couple of weeks. This server type idea, this is the process in a communicating processes or even a communicating sequential processes type of architecture or type of way of thinking. You can't just have a process that just interacts with the outside. Well, I mean, you can have a process that just interacts with the outside world, and you can have a process that just reads and writes global shared variables, but communicating between them with channels is a much more structured way of doing things. So we prefer structure because that lets us think about what the program actually does. So process just has inputs, it has outputs, those are the channels, and it has state, which are the local variables, and that's it. And when you start thinking about, okay, how do we actually organize the internals of this process, you will immediately realize that you've created an ad hoc state machine. And if you actually formalize it as a real state machine, or if you're just like, yeah, these are just some variables and we have a bunch of nested if statements, that doesn't really matter. Not initially at least, but eventually when you start trying to make something that is readable, then it starts to matter. And we're going to cover that in the future topics. So I'm just going to list up the future topics for this series of lectures, the things that we will cover. And you know what? I'm just going to put them all on the slide at the same time. So probably next time, distributed systems. The key realization we're going to have with distributed systems is that the only way to keep a system that is actually running all the time and is resistant to being separated into multiple partitions that can't communicate with each other is to just deal with it being inconsistent. It will have to be inconsistent at some level. But inconsistency means that data doesn't really matter, because data could be anything at any time in any place. And we don't like inconsistency for that reason, because we want our data to be meaningful. So the question is, how do we live with this inconsistency in such a way that we focus it exactly where it needs to be inconsistent, and we can manage to keep it consistent where we need it to be consistent, so that we don't get elevators picking up orders where there aren't any, or elevators not picking up orders where there are any, which is definitely a problem, because that would be some kind of inconsistency, right? Then we're going to cover state machines from first principles, exactly why we're making ad hoc state machines, but why does it make sense to formalize them as proper state machines? And the reason why is because it makes it impossible to express invalid data combinations. And we're going to separate our state machine into two parts. We're going to do that today as well, just to kind of get that started, but we're going to explain exactly why that is. And the reason why is because it makes our code testable. So the functional core is just, these are functions that decide what to do, but they don't actually make any changes. And since they don't make any changes, they don't interact with the outside world. And since they don't interact with the outside world, they're trivially easy to test for correctness. And then on the other part is the imperative shell. These make interactions with the outside world, but they don't have any logic in them. So since they don't have any branches, they don't have any conditions, they're impossible to test, but they're so simple that we don't need to. And then we're going to try to find out what is the boundary for a single task. We have a program that has a wide area of responsibility, and we want to separate it into multiple tasks so we can focus our attention on one thing at a time. But exactly what is the divide between these tasks? What is the divide between these modules? I want you to experience the problem of trying to solve that on your own first. But, you can see the literally subtext here. We're going to use the ideas of ownership and responsibility. So what is each task responsible for, and what data does it own? And if you can figure out what data does that own, what is it uniquely responsible for modifying, then you can more easily find the divide between different tasks. And we're going to talk about the differences between processes and objects in order to keep our interactions as explicit as possible. Because if we're keeping our interactions explicit, we're focusing on what are the real interactions in program, not just what are the possible interactions in our program. And if we can eliminate all the possible interactions, the only thing you're left with is the real stuff. And that makes our code more readable. And the final parts, probably going to be multiple parts, is going to be a code quality in terms of interactions. And we're actually going to analyze code quality in terms of its geometry. And we're actually going to take the code on the page, and we're going to draw color in parts, and we're going to draw lines between them, and we're going to analyze code quality from that angle. And that's not I haven't seen anyone do this anywhere else. I've seen a lot of people talk about the exact ideas that underlie this, but I haven't seen anybody take it like the extra obvious step and just actually draw it out on the page. But once you do that, you'll realize that all of the things that we're talking about in code quality actually have a very interesting geometric interpretation, which is pretty cool. But that's going to be it's going to be a while until we get there. So today, we're going to talk about error handling. And I have named the first slide "Error Handling Sucks," because it's true, it does suck. And we know that it sucks because, frankly, most code doesn't do it, and the code that does try to do it still doesn't do it, or it does it incorrectly. And so the solution to failing to do it correctly is to just don't do it in the first place. Here, let's look at what is the problem. What is the problem with our error handling, the traditional error handling that we're so used to? You're all C programmers, at least to some extent. Do you check all your error returns? I want some honesty here now. Who here has checked the error return from printf? Ever? Who here has checked the error return from pthread create? The mutex lock? Did you check that you were able to lock the mutex? Huh? Did any of you do that? Oh, we have one person who checked that. Wow, congratulations, that's 1% of you. Who has checked the error returns from sending and receiving both, or reading and writing to files or something like that? Yeah, nice, same person, of course. So we have one disciplined C programmer here, and then we have a bunch of let's call it lazy as a kind of a euphemism for efficient. You know, we're focusing on the code that needs to be done and not on the code that we don't want to do. And well, that's the problem, right? The error handling code looks ugly, and because it looks ugly, we don't write it. So it pollutes all of the happy path in our code. We have the things that we want to do, and then we have the things that we don't want to do, because if we were doing them, it means that something has gone wrong, and we don't want things to go wrong, so we just like, nah, don't. And the other part of the problem is that most errors don't really have a good way of handling them. So what happens if you're trying to lock a mutex and it didn't work? What do? Well, what did you do? That's actually a perfectly good result. You don't even remember, right? That's a perfectly valid result. There is no really good way to do, like what is the correct response to I was unable to lock a mutex? Try again? Crash the program and be like, well, that doesn't work. It's not worth trying again because it's probably going to fail again. So give up. Like, these are actually the only valid solutions. And you will find that in most of error handling, or most errors that can occur, the handling part of them is actually just try again. For some of them, it is undo the thing that just failed and then try again. But fundamentally, the only real solution to it didn't work is, or it didn't work and the program needs to work, is try again. Because if it didn't work and you give up, then the program doesn't work. And then we have a new thing that we are considering in this course that you probably haven't considered very much before, is that error handling only handles the things that you look for. So if you have unknown bugs, there is no error return for your algorithm being implemented incorrectly. There is no error return for cosmic rays, even though that would be very convenient, but that's not a thing that exists. And we also have another new problem, which is that we know that the program is going to crash eventually because that's just the nature of things. And because it's going to crash eventually, that is pretty close to the worst case scenario, is that it crashed, it burned, we don't know why, pick ourselves up from the ashes, try again. And if that's going to happen at some point anyway, there's not much point in fighting it. So if we need to handle that worst case, and the thing that we need to do is try again, then it might actually make sense to just crash the program, automatically restart it, and then it will automatically try again. So if we have some way of handling the crash, the solution to error handling might be as simple as crash the program. But that's only if we have the restarting mechanism. We have bigger problems than the standard, oh, it didn't work, here's an error. So we need bigger tools than just the error return or just the exception. So we're going to pull out bigger guns than standard error returns and standard exceptions here towards the end. So be prepared for that. Let's talk first, just to kind of get an idea of what is the cause of these errors. Let's just talk first about what is this generalized process in a process-oriented program. What does a thread do, typically? We have our ad hoc state machine. It has inputs, it has outputs, it has a for select loop. It has some initialization, and it has some state. So we're reading the state, we're writing the state, we're writing the outputs, we're reading the inputs. We have a loop so that it runs forever, and at the top of it all we have some initialization. We know that writing stuff is a destructive operation. Makes sense? If we've written stuff, we can't unwrite it. The only way we can unwrite it is if we have a backup somewhere. So we can't, and if we have a backup somewhere, the moment we write over the backup, then we can't unwrite that unless we have a backup, and then it turtles all the way down. So writing is destructive. That's kind of the point. But what is not destructive is finding out how, or finding out what you're supposed to write, and then I put how there as well. I'm not sure what I was thinking, to be perfectly honest with you. How do you modify things? You just write it. It's not that hard. That doesn't make a whole lot of sense. Okay. So finding out what to modify, what to write, what your next output is, and what your next state is, that is not a destructive operation.
You're stuck. You're stuck in whatever.
In Blackboard? Yeah. That's the internet for you. It says I'm fine now. You're still reconnecting. Yeah, that's the stable internet for you. That's high quality NTNU infrastructure right there. I literally cannot fix the router not working because it's up in the roof somewhere. So you're just gonna have to deal with it. It's sad. Right. So finding out what to do is non-destructive, but actually doing it is destructive. That's the point here. So let's consider in a generalized process, what can go wrong? Like, what are the things that could actually return errors that we can, at some point in the future, figure out how to deal with? And then, after we figure out what can go wrong, let's think about what should we do when it does go wrong? What is the appropriate response? Okay, so keep this in mind and have a look at this code. And hopefully it is of a font that is readable enough at the back. So on number 1, we do some initialization. So we're setting up some local data in some initial state. In number 2, we're receiving on a channel, or we're just receiving a message if we're not in a channel-oriented program. Number 3, we are finding out what to do, but we're not actually doing anything. We're just generating what our next state should be, and we are generating what our output should be. So this is a pure function. It doesn't read the outside world, and it doesn't modify the outside world. And then in number 4 and 5, we are actually modifying the outside world. So we're sending a message to another task, or we are writing to an output in the world, and we are overriding our state with a new state. This is just completely generalized. You're not going to be writing everything every time, and you're not going to be computing an entirely new output every time, but as a general concept, that's what you do. So this is done on, for example, the elevator example code that you get. You have a function called choose direction. It doesn't actually set the direction. It doesn't actually start moving. It just chooses the direction. And then after you've chosen the direction, you start moving. Or you have a similar function that asks, should I stop? But it doesn't actually stop. It just figures out if you should stop. And if you should stop, then it's up to you to actually stop. So these create something with functions that would be things like should stop or choose direction. It doesn't actually do anything. It's just a function. So what can go wrong? And after we figured out what can go wrong, what should we do about it? So let's go through these in turn. Number 1, the initialization. What can go wrong there? Well, something can go wrong there. If we're trying to initialize from an external resource, like we're establishing a connection to get an initial value from a database, or we're trying to read a file to initialize from a file, or we just started a program with low memory and there's no memory and so on. That could go wrong. So number one, definitely can go wrong. What is the appropriate response to we were unable to initialize? Is there any point in continuing after we were unable to initialize? No. Is there anything to undo after we were unable to initialize? No. What is the appropriate response? Try again. Make sense? Sending and receiving on a channel, done on operations 2 and 4. Can this go wrong? Well, any half-decent language or runtime will have no way for this to go wrong. If you're unable to communicate with the different tasks on the same program, you have some serious issues. So if this goes wrong, big problem. However, if we're talking about reading and writing the external world, for example, we were trying to set the motor output on the elevator, or we were trying to read the floor sensor or something like that, that could go wrong. But what is the appropriate response? We were unable to, or the goal of the program is to be part of the system that interacts with a human. And the thing that we're doing is we are reading and writing to the outside world. And if we are unable to read and write to the outside world, we are unable to perform the function of the program, and everything is broken. So what is the appropriate response to everything being broken? Try again. Because we can't undo the failure to write to the motor. How would you undo that? You have to compensate and try again. So that again, try again seems to be the solution. Then we have the pure functions that we wrote. Choose direction, and so on. Can that return an error? Yes, of course, but only if we make it return an error. So these can fail, but only because we want them to fail. Now the question is, why would we want them to fail? Well, we'll get to that. And then the final one, writing to local data. This is overriding our own local data structure. Now, if this one fails, then we are some serious, serious issues. Because if writing to a variable doesn't work, well, first of all, I can't think of a single programming language that will return an error here. Now things are seriously broken, so it's not even really worth considering. We've entered into the territory of, well, what if we nuke the entire planet from orbit? Now it doesn't work kind of territory here. So it's not, yeah, things are really broken if that is a problem. So what are the things that can go wrong? Well, unable to access the outside world. And what happens if our program is unable to access the outside world? Well, in order for the program to work, it needs to access the outside world. Otherwise, it just straight up does not work, because that's the point of the program. And so the only thing to do here is to try again. It's like, oh, our program wasn't able to work, let's just kind of leave. That's not a valid solution. The only thing to do is to actually try again. Let's think about it in terms of like classical errors. What returns classical errors? Like it returns an error or it throws an exception. The only one is really initialization. You can argue that reading and writing to the outside world could also return errors, but only again if we implement them in either the library or the operating system or so on. But yeah, interactions with the outside world, I should probably be more precise there, are the things that can return classical errors. And the only way to deal with unable to interact with the outside world is restarting at some level. Is it a full-on restart, like tear everything down and restart everything, or is it just try that particular interaction again? It could be either one. It really needs to be determined on a case-by-case basis what is the appropriate solution, because restarting everything is definitely aggressive. But again, it's a thing that we need to handle anyway, so we could just merge all the possible failures into a single failure, which is it crashed for unknown reason, because we need to handle that anyway. As for these pure functions, we can make them fail intentionally. So we can add our own asserts, our own throws, our own panics, our own error returns. We can add those. The question is, do we have any good reason to do that? Because again, if it doesn't work, then the only thing we're communicating here is that it's not going to work. So the thing that we would have been writing to the output would have been wrong, so we don't even try to write to the output. So yeah, we can add our own stuff there so that we force the program to try again. But that's about it. And the thing to realize here is that they don't really add themselves, right? So we need to think about, should we communicate to the process via our functions, return or throw, that it is not worth considering the result of this function and it should try again? That's what adding our own failures would do. So consider, what do we do with that information that our own functions fail? Well, I just said it in the previous sentence because I don't even remember the contents of the next part of my slide. The only thing we're communicating is that we were unable to, if you continue from here on out, it's going to fail. So don't continue from here on out, try again. Right, so this is the conclusion for all of the standard error handling. And also the non-standard error handling. The only thing an error return communicates to us in this kind of program is it's not going to work if we keep going. You need to do something else. And the only thing that is something else that you could do is try again in some way. If that means crash and let another node take over, that's trying again. That's a valid solution. If the solution is don't crash, undo some work, start from the place where we undid it, and then keep going from there, that's also a valid solution. But fundamentally, the only thing that we can do to handle errors is to try again. So that's the error handling part of errors. And I think this keeps getting confused in a lot of programming courses or tutorials or whatever. They talk about error handling. And when they say error handling, it's check the error return and it's up to you from here on out. And checking the error return isn't error handling. And forwarding the error so that someone else can handle it higher up the call stack, that's not error handling, it's just error forwarding. So error handling, what do we mean by actually handling the error? We mean trying again. That's fundamentally the only thing that is usable. So what do we need? In order to actually handle errors and not just like look at them and be like, ooh, pretty errors. We need, of course, a robust way to detect the errors. So we need some way to look for all of the things that go wrong in our program, or all the things that would cause something to go wrong in the outside world. That means, of course, detecting all the errors, and it also means detecting all the errors that we can't detect. Right? Wrap your head around that one. Cosmic rays, it's an error, we can't detect it. We need to detect it. How do we detect it when we can't detect it? Fun times, right? So we need robust error detection, and it needs to be so robust that it detects things that we can't see. That's not, and it's an easy problem to solve. Because you can only find what you're looking for, so stop looking for errors. Now we need some way to crash the program so that we're able to, or some unwinding mechanism. But a way to crash the program is definitely the easiest thing to do, because how do you crash a program? I mean, everything has an exit function, so you just use that. We need a restarting mechanism. That's what the process pairs are for. That's what the exercise is about. or you could do it with supervisors. And I'm not going to talk too much about the differences between them or the benefits or drawbacks of each because, again, that's also part of the exercise and I want you to think about it. And then optionally, this isn't strictly necessary, but it might be useful in a lot of scenarios in order to not be so aggressive that you restart everything every time because, again, might be a bit overkill. Some way to save progress so that you don't lose all of your previous work. Now that also might not be necessary even if you do crash. For example, again on the elevator system, what happens if a single elevator crashes? Someone else takes over. So you haven't lost any progress because somebody else took over. And then when you're restarted, well, you need some way to add a new node that's completely fresh from the system that doesn't know anything. And what is the difference between a restarted node that has amnesia and a new node that is fresh? Well, there is no difference. So if you're able to add a new node, you're able to add a restarted node. And if you're able to deal with losing a node, you don't need to save anything. So it straight up just might not be necessary to have any temporary saved progress at all. But sometimes it is. So it's a case-by-case basis again. We have a slide break here with a title, and we've gone for 45 minutes. So 15-minute break. We have the situation now where we have, we need the robust error detection that can detect errors that we can't detect. And the question is, how do we detect these undetectable errors? Let's just think about what is error detection, like what are we doing? We have we have two absolutely giant problems that we need to solve here in terms of error detection. The first one is that error detection mechanisms can have errors in them. So we can fail to detect failures. And that comes to we're only looking for or we can only find the things that we're looking for. And if our vision is impaired, then of course we can't find errors. So even if our error detection mechanism does work flawlessly, even if we don't have any flaws in our ability to find and report errors, we're going to miss out on stuff because we're not looking for it. So we need some way to look for all of the errors, and the more code we add to look for errors, the more code that needs to be debugged, and the more code we introduce that might have bugs in it. So this is not a sustainable way to do error detection. Because there are no error returns for bugs. If we write the algorithm incorrectly, that doesn't give us an error. If we use the wrong variables and it still compiles because the type checker says okay and it's, the program is still valid, it just does the wrong thing. Or another kind of bug, which can we really blame the programmer? Not necessarily always, but if we misunderstood the specification, is that really a bug? Like, it's more that, oh, we didn't think about that this is what the program has to do. I mean, it does everything that we thought about correctly, but the things that we didn't think about, it doesn't do those, maybe even at all. So does that go under bug? Maybe not, but you get the idea. Then we have anything that's timing related. There is no error return for, oh, the order of operations was accidentally the wrong way around here this time because that's just random. And this can cause, this is a thing that, because it has to do with the random ordering of things and the random timings and so on, it's not going to appear very often. It's something that only happens like once every 100,000 times or something like that. And so when we're when we're debugging the application and testing it, it's not going to show up. And then you start sending it out into production and you have 100,000 users and it shows up immediately. And anyone who's ever played a video game on release day will know about this. And of course, there's no error return for truly, truly random stuff like cosmic rays. So we have this problem that random events are also very hard to debug because of their randomness. And why are they hard to debug? Well, it's because we can't write tests for them. because tests are fundamentally, by their nature, not random. That's kind of the point. We want to be able to create an infrastructure or create a scenario that is the same every time, so that when we're trying to make the code work, where it's not just going to be like randomly this time it didn't work because tests are random. So just because tests are non-random, and that's the point, so that you have a consistent baseline, so you're not building your program on shifting sands. Testing things that are random becomes very hard to debug. So instead of looking for failures, we have this problem that we can fail to find things that we're looking for. So instead of looking for failures, we look for success. So what do we mean by this? How does this look like in the world? Well, it's the same as before, really. But instead of trying to go, yeah, this looks like it's not going to work, you try to find situations where you can instead go, this looks like it is going to work. And then you pass that through instead. So you're looking for, does this result seem like it is valid enough that we can continue executing? Does that make sense? Instead of looking for, this looks bad, you're trying to look for, this looks good. So you're validating the result and going, yep, we can continue. The result that we return from the function that goes what to do, we can do that. And doing that will not produce an incorrect result. We have the same problems as before as well, in that if we wrongly identify success, it means that, we go, it does not look like this is going to work, but it would have worked. So we can wrongly identify success, and that means it would have worked, but we reject it. So we're rejecting things that would have been valid. And the question is that a problem? Is rejecting things that would have been valid a problem? No, it isn't really. Of course, if you tune this too hard, so you're only accepting a very small subset of things that would work, and you're rejecting a lot of things that could have worked, then it might be a cause for concern, but ultimately this is not a problem, because it is better, after all, to be safe than to be sorry. So if we reject things that would have worked, then we go, no, that's not going to work anyway. Okay, so what? Try again. We get something that does work, we continue. So the fact that our success detection mechanism might be somewhat broken is not a problem, and definitely not a problem of the same magnitude as our failure detection mechanism being broken. It's, no, never mind. So this idea of creating a success detection mechanism instead, this is the idea of the acceptance test. So let's think about error handling in like the traditional non-handling way, I suppose. So just grayed out in like, just keep this in mind, of course. We want to handle the most of our errors before we ship our code, right? So we do want to test our code, we do want to debug our code. We just don't just write in the blind and then ship it and see what happens. Like, yeah, move fast and break things, but maybe don't move that fast and break that many things. So, during our testing phase, detect as many things as possible, of course. We're going to get back to how to do that. But after we've done with testing and we've produced our code and we've delivered it and it still doesn't work because that's just the nature of things, we need to detect our errors at runtime with acceptance test. So are we detecting errors? Yeah, kind of. We're just rejecting everything that doesn't look good enough. And we consider everything that doesn't look good enough as errors, even though it might technically not be an error. The thing with acceptance tests is, because they just say, yeah, this doesn't look good enough, they don't necessarily give you good insight into exactly why it ended up being not good enough. Kind of backtracing the function in order to find out why exactly this gave you the wrong result or an unacceptable result. Programming that in such a way that it does give you good insight good enough insight that you can conditionally find out what is the appropriate response to it at runtime, that's a hard problem to solve. And again, it's not strictly a necessary problem to solve because it didn't work. What's the result? Try again. How do you try again? Crash the program, automatically restart. It tries again. So it's not necessary to do this, but it's a thing to notice that acceptance tests just say, it doesn't look good enough. We don't necessarily know exactly why that is the case. Again, the only reasonable course of action is try again, so it really doesn't matter. So here are the two ways out of error handling. The aggressive way, full restart. Again, might be overkill, but we know that it works. So we merge all of our error modes, all of the things that could go wrong. We go, it doesn't really matter exactly why it went wrong. We don't really care. We crash the program because that's the worst case scenario. And we need to handle the worst case scenario anyway, so why not handle everything as if it is the worst case scenario? It will work. It's aggressive, but it will work. And the other way out is to, okay, let's try to roll back a bit more gently, undo a couple of things, and then try only those things again, not try everything all over again, but just try all the couple of things that seem to not work out again. This seem reasonable? Instead of looking for failures, we look for successes. When we find out something that looks like it's not going to be successful, we go try again, either try everything from scratch or try a little bit. So what are the mechanisms in code? How do we actually program something like this? What does it look like? And I'm not going to go into way too much detail about it, but what you need to know is that it really does just use the same mechanisms as classical error handling, right? An acceptance test that fails is we take the results and we run it through a function that goes, is this a good result or is this a bad result? What is the content of that function? Up to you. You need to figure out what does it mean for a result to be a good or acceptable result. And in order to figure out that, you need to look at the specification and go on a case-by-case basis. What does a good result mean? So for example, the should stop function. You're at the top floor. Is it appropriate to not stop on the top floor? Right, of course, so you need to think about it. That's a condition where the only acceptable result in that case would be yes, stop at the top floor. Or you received information that you arrived at a new floor. You were at the bottom floor. You received information that you have teleported to the top floor. Is that an acceptable result or should you ignore it? It makes sense to ignore it. So these are pretty trivial examples, but when you get to more complicated examples or more complicated scenarios, like we are overriding the order state of the system. We received some new information from the outside world, from the network, and we have some new orders. And we have some old orders, and we're trying to override the data of what are the orders in the system. What is the appropriate, what does it mean for that operation to be successful? Well, if we had a bunch of orders and we received a new order and now suddenly we have fewer orders, that might be an unacceptable result. So that means that we have a bug in our code that just randomly deleted a bunch of orders. So that's, again, a fairly trivial acceptance test. So you just need to think about what are all the things that means that the result is successful. And if you have an unsuccessful result, throw an exception, return an error, doesn't really matter. How do you handle the exception? You just straight up don't catch it and the program terminates. Or how do you handle the error return? Well, if you have an error, kill the program. I would argue that exceptions are superior in this case for, I believe, two reasons. The first is that you can't ignore them, which also means that you can't forget them. For those of you who have written some Go code and you have this if error, blah, 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 if error, blah, 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 it's very tempting to just straight up write an underscore as the error in order to ignore it and then just don't have the if error do something because it's a pain in the ass and the code looks ugly. With exceptions, you don't have that problem because what happens if you don't catch an exception, it goes uncaught, it bubbles up to the top of the call stack and it terminates the program. So because So the first is you can't ignore them, and the second thing is they do the correct thing, which is kill the program. So after we've killed the program, we need some way to restart it. This is where the process pairs come in, as one of two possible approaches to restarting the program. The first approach that we're not going to talk about in great detail here is the supervisor. This is the kind of the, not the inverse, definitely not the opposite, conjugate to process pairs. So the supervisor is a separate program that goes, oh, the main program died, I need to restart it. This is fairly intuitive, right? You have a separate program that monitors, am I getting a response from the main program? And if we stop getting a response from the main program, it means it has either crashed or it has just gotten stuck and it's become unresponsive. And if it becomes unresponsive, we don't hear anything from it, we automatically restart it. So the supervisor performs the restarting. Erlang uses this approach internally in its runtime. So you can create a tree of supervisors and they will automatically restart the sub-processes if they die. And if one sub-process dies, you can restart all of them or just the one, or you can restart them in order, or you can restart them in random order. Fundamentally, this is a really useful mechanism, and Erlang has been like, oh, we're making robust code, we're putting this as part of the language itself, really, and gone supervisor trees. So if you're an Erlang programmer or an Elixir programmer, use supervisor trees. It will perform all this restarting business for you. The other way is to, instead of having two separate different programs, you just use the same program again, hence the pair in a process pair. So the backup program creates, or the primary program creates its own backup clone. It's the same program, it's a clone, which means that the program has two phases. It has a backup phase, where it's just listening for, does the program exist? And then it has a primary phase where it actually does the work and signals to the backup that, yep, I'm still here and I'm okay. So the backup will take over when the primary dies, and then the backup will become the new primary and create its own backup. And this will continue in a cycle. In the exercise, and I'm not sure if I have it in the slides as well, exactly what is the structure of a process pair program, the primary phase and the backup phase. I think I have it in the slides in a couple of slides from now. So I'm not going to do more about that now, but if I don't, I will have to improvise, so that's okay. Now, a question that I do pose in the exercise is, what is the advantage or what is the disadvantage of the two different mechanisms? So in the supervisor way, we have two different programs, and in the process pair way, we have only one program that has two different phases. Well, one of the differences between them as well is, how do you save data so that you can transfer some amount of data from one node, or from the backup to the primary, or from the primary to the backup, so that when the backup restarts, it doesn't restart all the way from scratch, but it can start with some amount of progress. That might be useful, it might be not useful. Oh yeah, I did have a slide about the program structure. Here we go. A process pair's program structure. First, in the backup phase, listen from activity from the primary. Here's the thing that you need to think about and be aware of, and it should be fairly intuitive. A dead program can't tell you that it has just died. Right? So you can't send a signal that, oh, I have been killed, please take over. That's not a thing you can do. You have to do it the other way around. So you have to instead go, yep, I am alive, I am working, here's some data, this is fine, I am still here. Continuously send messages, and then when you stop hearing messages, it is implied that it has died. So you cannot send the I have died, I am dead now message. That's not a possible thing. You need to instead send I am alive messages. So when you are starting in backup mode, you need to listen for, is the primary still there? And if the primary is still there, you just sit there and wait for it to die. When you no longer hear from the primary, you assume that the primary is dead, which means that since it's dead, we need to become the new primary. And in order to become the new primary, we need to do two things. First is to create the backup clone so that we have our own backup in case we die. And then the second thing is kind of transition from backup mode where we're listening from activity and transition into primary mode where we are doing the actual work and then sending some activity to the backup so that it knows that we're alive. So there's constantly communication between the backup and the primary. Once the communication is broken, it means that the backup should take over and become the new primary. And this continues in a loop. Does this make sense? I think actually I'm going to improvise here a bit, and I'm going to pull up the example that I have of this in action, so you can see what it does in action. Oh, full screen. Here's the process pairs demo. So you can see what this program this is the program that you will be making on the exercise. So we start the program. It starts in backup phase and goes, there was nobody there. So it starts a new backup and it becomes the primary. Then we terminate the primary. The backup becomes a new primary and it starts its own backup. We start the second one. A new one takes over. And in order to kill this program, you need to kill the backup first. Because if you kill the primary, it's just going to start a new backup. Make sense? I am not even logged in, and it's like, yeah, you want to watch Dr. Campbell now. I guess people who use Chrome on an old laptop on a university network definitely want to watch Dr. Campbell right now. So I don't know why. Curious. So such is the world of cookies and advertisements and so on. Anyway, does that make sense? Cool. We have one last thing that we need to do for process pairs in order to have a full functionality, which is, well, it's the optional part. And the optional part is sharing the data so that we can restore, so that the backup can continue where the primary left off instead of starting all the way from scratch. And there are three main ways to do this. But yeah, why would we want to do this, first of all? Well, the reason why is because so that we don't necessarily want to restart all the way from scratch because it's a bit aggressive and we might lose some progress there that's worth having. Now, there's also a perfectly valid argument that if we do lose that data, well, since that data is data and data needs to be stored and the storage can fail, there's definitely an argument to be made that, well, if the storage fails, then we need to be able to compensate for the storage being lost, and so it needs to be possible to perform a full restart, the full-on aggressive restart. And since we need to perform the full-on aggressive restart, it might make sense to just not have any saved data at all because we need to handle there not being any data saved. So there's definitely an argument to be made for this is not necessary. But it might be a useful thing to have because, again, the most aggressive solution might be overkill. Because if removing all of the data and starting from scratch means that the thing is kind of half dead for 2 minutes while it gets back up to speed, that's, not optimal. So we have the challenge here. We need to send data from the primary to the backup, And then the backup, when it restarts, it needs to be sure that this data that it gets is good data. Because if it gets bad data, it means that the backup is going to go, oh, this data is bad. And if it's working with bad data, it's going to fail an acceptance test. And then it fails an acceptance test. And then it goes, well, that failed. We can't continue because the data is bad. And then it kills itself. And then it spawns a new backup. And then the backup goes, oh, this data here, looks like bad data. And then it fails the acceptance test. And it kills itself. And and now you have an infinite loop where you have bad data. So you need some way to check that, this data is good data. Otherwise, you'll immediately crash and you're stuck in an infinite loop. And that's also a fairly decent argument for why you shouldn't save data in the first place, because what do you do when you have bad data? If the data can be bad, then what's the point of data? So, again, sharing data, not strictly necessary, but it might be a useful thing to do if you're able to do it. So here are some non-technical terms for why you might end up with bad data in case you're doing this and you need to write an acceptance test to figure out what is good data. Just some ideas to think about. If you have two pieces of data from two different places, they might be out of sync. Which one is valid? If you were partially writing data when the program crashed, how do you make sure that the data you're restoring is valid? So it might just be straight up corrupted. If you are restoring data from two different threads, and they need to kind of be in sync in order for the program to work, and they were at different levels of progress, like they're done different amount of work, but so their data between them is out of sync in some way. The data might just not make sense yet because it was not finished, or you didn't have a synchronized checkpoint. So yeah, these are not technical terms, but these are just some reasons for why you might end up with bad data. So it's worth thinking about if you're going to start restoring from, like when the backup is taking over and you want to check, is this data good? These are some of the things that you need to consider. But again, for the exercise, what is the data? The data is an integer. How many ways can an integer be bad? Well, it's an integer, so either it is a number and the number is valid, or it is a number and, well, the number is always valid. So there's no way for a number to be bad data. So in that case, the acceptance test is return true. That's a perfectly valid acceptance test. So here are the three approaches to sharing. I'm going to put them all on the same slide immediately, I think. The first one is probably the most obvious. You write to a file and then the backup restores from a file. It's definitely an easy way to do. An alternative to this is to, instead of writing to a file, you write to the other nodes, because you probably have a program with multiple nodes in it. And if you have a system that lets you share data between nodes so that the other nodes can take over, then writing to a file is kind of pointless, right? Because you already have the functionality to distribute the data across the nodes, and you already have functionality to restore data from the other nodes when you connect a fresh node. So in that case, and also for this elevator system that you're making, file storage here is not necessary because you've already stored it remotely, and that gives you multiple nodes it's stored to instead of just a single node, which is the one that had a program that died on it. And if you're storing data to the node that had a program that died on it because, for example, it lost power, then the chances that you have corrupted data is fairly high. So storing to a file on the same system is definitely a worse way to do it than storing the data among the other nodes. But this does assume that you have reliable storage, but you will, because you have other nodes in the system, and if you're able to communicate with them, you have reliable storage there. The other is to send the data as part of the I am alive message. So the primary needs to communicate to the backup that it's still there. And a message has two pieces of information. The first is that you are sending a message. That's a piece of information. And then the other piece of information is the content of the message. So we can abuse the content of the message here to send the actual data from the primary to the backup. So in this case, for the exercise, start a network connection on localhost, and then the data that you're sending is the value of that integer. So That's a fairly straightforward way of doing the I am alive message here. And then the third one, which we are definitely not going to do here unless you are an experienced Erlang programmer, is to do it the stateless way. So let's say we have a database, and we have a shared database, and we have all of the infrastructure that gives us a shared database that exists on multiple nodes. And the best way to do that is to use whatever language infrastructure and library infrastructure that we have, which means, again, only do this if you are a moderately experienced Erlang programmer and you know how to use Amnesia or something like that. And in this case, we don't really need to have any local data at all. It's just temporary data. All our local data is just a temporary. We are really just reading and writing to the database, and the database handles, in its infrastructure, handles all of this with common storage and all of the messaging and all of the communication and all of that in the background. So alternative 3 is really combine alternatives 1 and 2 into a library and do that instead. But if you have that library, cool, use it. But if you don't, I wouldn't suggest trying to make that from scratch, because that is, well, you don't have time for that, straight up. I will mention also finally, in terms of process pairs, a within program restart, because your program is probably going to consist of multiple threads. And the reason why your program crashes is probably because a single thread had a problem, not because all of the threads had the same problem at the same time. That's very unlikely. So the question is, how do you detect that a single thread crashes? And are you able to make it so that when a single thread crashes, it crashes the entire program? Or if a single thread hangs and doesn't crash, how do you detect that? And if it does happen, are you able to restart a single thread, or do you have to restart the entire program? I'm not going to give you an answer to that, because case-by-case basis. There is no correct answer to that. But I would say be careful here when you're trying to think about this. If you do it, try to implement it. Because the more code you add, the higher the chance that you've added buggy code, just by virtue of more lines equals more bugs. So if you're spending a lot of time writing code that handles single thread restarting, and you need to write that infrastructure yourself, just be aware and consider, is it worth spending the time to solve this problem, or is it worth spending some more time trying to fix normal bugs the normal way? And that's just, what is the correct thing to do? The correct thing to do is do both, but time is a limited resource here, and you need to spend it appropriately. Right. That was it about crashing, the aggressive way. Now let's do it the less aggressive way. Let's do the partial undo. Let's do the partial undo in the standard error handling way. So we're going to take our error returns, we're going to take our exceptions, and we're going to go, how do we undo some work that we did and then try again? And how does this look like? What does this look like in code? And are error returns and exceptions enough, or do we need to pull out the bigger guns? And, well, spoilers, we need to pull out the biggest guns we have in our control flow inventory, because this is not something that is, this isn't easy. It isn't easy to make code that actually handles errors and doesn't just like look at them and go, ooh, pretty errors. Consider that a lot of programming is just this. You have a sequence of operations. First you do A, and then you take the result that you get from A, and then you do B with that result. And then after you've done that, you do the C thing. So, open a network connection, read some data, and then after you've read some data, maybe write some data or figure out that you need to read some more data. So like read account information and then read posts or something like that. It doesn't really matter what it is. So maybe we fail to establish a network connection to our database, or we fail to retrieve information for that user, or after we've retrieved that user, we fail to retrieve information about what they've have on their account or something like that. So multiple things can fail there. Or maybe we're opening a database, adding a row, and then adding some content to that row. And if we were unable to add some content, we need to unmake that row in the database, because otherwise we have an empty ghost row that just has nothing on it. Does that make sense? If we do something, we might need to undo it. Otherwise, we might have some temporary stuff that is just kind of ghost town that is left there forever. We allocated some memory, we have leaked some memory, for example. So the question is, how do we undo this? If do C returns an error, and we need to undo A and we need to undo B, how do we do it? Well, the first thing that you did probably is learn about error handling. And I put this in quotation marks because it doesn't handle a goddamn thing. And that's what this is. You know, your classic if error, return error. You're all familiar with this. You've all seen code that looks like this. You know, if something goes wrong, return the error. Now, this doesn't handle any errors. Because what was the problem with the error? The error is we were unable to interact with the outside world. If we were unable to interact with the outside worlds, or our interaction with the outside world failed and it needs to be undone, what is the appropriate response? Undo it and try again. That's what we're aiming for. We're aiming for undo and try again. Now, this just tells us that it didn't work. It doesn't undo it, and it definitely doesn't try again. And we're going to focus on the undo part, because the try again part, well, let's just run the function again. That's not all that hard. So this is wrong, right? It doesn't undo anything. And also, I would argue more importantly than being wrong, it is truly disgusting. We had 3 lines of code, and now we have, 15 lines of code. So it is wrong, because it doesn't do the undo. So let's add the undos. So let's actually add the undoing so that this is, at least we can make it correct, hopefully. So if we have an error, we not just return the error, but we actually undo it. We're ready? Let's add the undoing. Oh my goodness, the code is starting to get small in order to fit everything on a single page. We had 3 lines of code. Remember that. We had 3 lines of code here. And we added error detection with error returns, and then we added undoing. And the code the font keeps getting smaller because we need to fit more and more on the page. But hey, at least this is reasonably correct, right? If we get an error in the last block, we failed to do C, then we undo C, and then we undo B, and then we undo A. So at least this is correct, right? Yeah, sure, it is correct, but wow, this is starting to get really bad. So traditional error returns, it doesn't really help us with the undoing problem. Yeah, sure, it returns an error. I guess that's nice, but it doesn't help us. It doesn't do anything for us. We need this undo. And we also have this problem that all of this error handling code, the error handling code is supposed to be the unimportant part. It's supposed to be that, yeah, okay, in case something goes wrong, just by the way, do this, right? That's not the main flow of the program. The important part of the program here is do A, do B, and do C. And it is 1/5 of the code. No, it's 1/6 of the code now. And when the important part of your code is 1/6 of your code, yeah, this is not great. So let's try it with exceptions instead and see what happens. Is it better with exceptions? Yeah, maybe a try catch. You're all familiar with this, right? You see the problem? You're all familiar with try catches, right? Do you see the problem?
If A fails, we still try to undo C.
Yeah. So this is wrong, right? We're undoing all of the things even though only one of them goes wrong. So we need to undo only the correct ones. So let's do it with exceptions again, but this time for sure, we're back in hell. We have all this repeated code again, where undo B occurs 2 places and undo A occurs 3 different places. And if we forget one of them, then we're fucked, right? So it's at least, hey, at least success, it's correct. Also, I would consider this to be not safe for work. So it is definitely still ugly. So let's try exceptions this time and get rid of the repetition. Wow. So this is, still progress, this is correct. And the repetition is gone. So the ability to fail to undo the correct things in the correct order, that's sorted out. It's also even uglier. So like, I would consider this to be what we would call a career limiting move. But look at this. Again, let's preview code quality here. Look at the geometry of the situation. We have do A and we have undo A. And look at how far apart they are. Do B and undo B, far apart again. Do C and undo C, far apart. They're also in different scopes and at different levels of nesting. Now they're the same levels of nesting. And we also have the problem that our code has the shape of like a triangle of doom. It's like a phalanx coming in from the left side and pushing all of our code over to the right. I don't know who has heard the expression that good code is communist code because it leans hard to the left. Right. So this is not terribly good code. You can see that we have the same problem again here. Like we have 3 lines of code: do A, do B, do C, and we wanted some undo functionality, so we really want 6 lines of code. That's all we want. And this is most definitely not 6 lines of code, and it is 4 levels of nesting deep, or is it 5? I've lost count. So this is not great. So back to the title again, right? Error handling sucks. Proper error handling does require the undoing. And without the undoing, we're not actually handling the error, we're just kind of, oh, look, error, pretty. And we have the problem that both error returns and exceptions produce catastrophically ugly code. It's not like, oh, it doesn't look nice, but it's like it looks so bad that trying to work with it is a pain and suffering and madness. So in order to do this correctly, the appropriate response to that is to be like, fuck this, I'm not touching error handling. We're just skipping over that part. And that's when the appropriate response is to go, nah, I'm not even going to try, then we have a problem. And that's why we prefer the restarting everything from scratch mechanism, is because trying to undo a couple of things is actually really, really hard. And what happens if we crash in the process of undoing something? Well, now we're back to having to restart everything anyway. So this kind of error handling is definitely not ideal. And if the code has to look like that in order to do it, yikes, big yikes. So in order to do this appropriately, we need some bigger tools. We need some seriously bigger tools than just error returns and exceptions. We need some bigger tools than try-catch boxes. We need some bigger tools than ifs and our elses. And those bigger tools, that's what we're going to pull out on the last part, and it's not going to be the full 45 minutes after the break, but we are going to take the break. And after that, we're going to talk about control flow mechanisms. Let's just kind of context switch back, recap a little bit, keep our attention where it needs to be. So we had an error, and we detect our errors with acceptance tests because it's better to detect success than to detect failure. And when something goes wrong, the only appropriate thing to do is to restart. And we can either be aggressive and restart everything, or if we don't want to be fully aggressive and restart everything, we need to restart a couple of things. And when we're restarting a couple of things, then probably we will need to undo something. So error handling comes down to optionally undo something and definitely try again. And we are now stuck with this, how do we undo something and use the control flow mechanisms that we have on hand, error returns and exceptions, try catch. our if statements, how do we use those to conditionally undo the correct things in the correct order at the correct times? And we have so far seen that our if-else is not enough, our try-catch is not enough, triangle of doom code. So we need some bigger tools than these. So we need some more advanced control flow mechanisms. So let's look at the problem. Let's actually visualize the problem. With error returns, or with exceptions really, any function that takes some input and returns either a successful output or a failure output has conceptually two paths out of the function. So our A function, our do A function, it can return an A or it can return an error. And our do B function, it takes an A and it can return a B or it can return an error. So you see these two paths? The blue paths are the error paths that come out of the function. Again, a preview on the code quality. Let's look at the geometry of the situation. What we want to do is we want to undo C, undo B, undo A. And our code path goes from left to right here, because that is the order in which we read text in our language here. And we want our error paths, these are coming out the bottom, and we want to have something that goes backwards. So we want control flow that goes backwards. And frankly, most code goes forwards on the page and it doesn't go backwards on the page. So we need some way to go forwards but also go backwards at the same time. So, okay, let's look. What can we do with these error returns? What are our geometric options? What can we do? Well, the first thing that we can do is kind of just group them together. So we have multiple different errors and we don't really care what the different errors are. This is what we did in the first C code example. Like, we didn't actually handle the error, we just kind of forwarded it so that if there is an error, we just feed all of those and we put them in a super block and it returns either a successful C result or an error, and we don't know what failed and what needs to be undone. So this is error forwarding. It doesn't actually handle any errors. It doesn't do anything. Some of you have probably seen languages that have syntax for this. For example, Rust has the question mark operator. I don't know if you're familiar with this, but these kinds of operators, they just forward the error. They just say, okay, if it failed, return the failure, otherwise continue down the chain of functions. Again, it doesn't handle the error, just error forwarding, so it's not what we need. So we need something bigger. We need a backwards path. And preferably, it would be nice if this path was actually backwards on the page, so that the code goes down the page when we're doing and it goes up the page when we're undoing. That would be ideal. The question is, what control flow mechanisms do we have that actually let us write code that runs backwards on the page? So what we really want is something more like this. Right, we want to be able to pass the control flow, the error control flow in blue on the bottom, we want to pass that into the undo functions. And then we want to have some kind of visual relationship between the do and the undo so that they're close enough on the page. So we don't have do A at the top of the page and undo A like 600 lines below it in the catch block. We want to keep them close so that we can't mess it up, so that it looks nice. Because code that looks nice is easier to read. If it's easier to read, it's easier to understand. If it's easier to understand, it's easier to write correctly. The question is, how do we do this? Well, let's first do it with error returns. The classic C style. What is the biggest control flow gun in the control flow inventory in C? If, nah, weak sauce. Switch, garbage. Function calls, they're pretty cool, not cool enough. We need something bigger. What we need goto. We need goto. Here's how you would do it in C with gotos. Now these, they're not on the same lines. They're supposed to be under each other, but, font size, keep it large. Do A on line 5-ish. If we have an error, go to undo A. Right? So the do and the undo are at least here visually close to each other. but the act of actually undoing it, they need to be nested forwards on the bottom end there. So this is closer. It's closer to what we want, but it's not super perfect. This is better. Here's a challenge for you. This is a challenge that we've seen many attempts at. Try to make something that is less error-prone, so that, in error-prone I mean so that you can't forget to undo the correct things in the correct order. More readable, so that you understand that when you have an error, you go to the undo phases. That doesn't have a repeated code, so you don't call undo x multiple times in different places. And that doesn't use goto. Because if you're able to solve this problem, you should talk to the Linux developers and tell them to change this kind of structure in their source code in all of the places where it appears, and it appears many places. This is the standard pattern for doing and undoing in the C code with error returns. And now you might be thinking, well, goto. I've heard that goto is considered harmful and that you shouldn't use goto. Who here has heard that you should not use goto? Right, and the question is, well, who said that and why did they say that and how did it become a meme? Where did goto considered harmful come from? So it's from this famous paper by Dijkstra. He wrote a paper called Goto Statement Considered Harmful. The question is, when did he write this and what did he mean? Remember, this was written in 1968. This is written before structured programming. This is written before C as a programming language was even invented. This is written arguably even before functions were invented. You just had labels, and labels were like a block of code has a label, and then that's kind of that block of code, and you can jump around anywhere at any time to any label in any place for any reason, and those could be anywhere. So go to used to mean jump to literally anywhere halfway through a labeled block of code, like halfway through what is conceptually considered to be a function. You could jump there from anywhere. So it's not just a labeled goto within a function. It's not just a scope like it has to be in this constrained box. This is where our goto could be in. The gotos were like, it could be 600 lines away, it could be 1,000 lines away, it could be 100,000 lines away. It could be anywhere. And that's largely because functions really weren't a thing yet when this paper was written. So what Dijkstra meant when he said goto is considered harmful was, if you are randomly jumping around in the code in a completely unstructured way, you're going to make a mess. Please don't do this because it makes your code completely unreadable. He also said this: I remember having read the explicit recommendations to restrict the use of the goto statement to alarm exits, error returns, but I have not been able to trace it. Presumably it has been made by Tony Hoare. It's easy to remember his name because all his first names have contractions. So it's Charles Anthony Richard Hoare. So Chuck Tony Dick Hoare. What a name. So the explicit recommendation in the paper titled Goto Statement Considered Harmful is to use goto statements in this way that we just did. This is exactly what we are doing. So we are using goto in the one way that the paper that says don't use goto tells us to use goto. The question is, we've all been exposed to this. You read the title and then you don't read the content and you go, the title is the only thing I need to read. And then such is the life of a meme. A meme is born, goto considered harmful, never use it. Of course, that's not what we're supposed to do. Now we need to consider exceptions. I have said that exceptions are better because you can't ignore them, and then they do the correct thing, which is terminate the program if you don't catch them. What happens if you do catch them? Well, they can still do the correct thing. Here is the way to do it with exceptions. Now this requires that you have some either some very inventive programmers that are able to perform black magic, or you have a language that has this as part of the language. Scope guards exist natively as a part of the D language, and it exists with dark sorcery in C++11. What is a scope guard? A scope guard comes in 3 variants. Scope exit, which is do this when the scope terminates, so when the function returns, do this. Scope failure, which is when something goes wrong, an exception is mid-flight, do this. And scope success, which is when there is no failure, do this. Scope exit, scope failure, scope success. What would the do and undo code look like if you had scope guards? Well, it would look like this. This is the ideal solution to this problem. This is the hardcore, non-conventional, backwards control flow mechanism that we were looking for. If B throws an exception, then there will be an exception that's in flight. It will start unwinding the stack. The first thing it encounters is the scope failure undo B, because we're starting to unwind the stack. So we have, on the stack, we have a scope failure statement. And then we'll undo B, and then we'll keep unwinding the stack. It will find another scope failure statement which says undo A. So this does the correct thing. If you've written go, you've maybe encountered the defer statement. Defer statement is the same as scope exit. So it doesn't look if there's an error in flight or not. It just does it if there is an error or no error. But we want scope failure specifically. So you can do this in D. This is D code here, right here, or you can do it in C++11, where you need some, frankly, insanity-inducing template magic to do that. But it is possible, because we're kind of looking at the stack frames and finding out what exceptions are in flight and assuming that there's only one, which is correct, and then using that one, and then using some GCC extensions to kind of, no, we're not doing that, we're using the RAII patterns, and yeah, it's fun, but it's also, you need to have a solid grasp of the C++ language in order to understand exactly how it works. But it exists, so you can do that. And those are the only 2 places I have come across where you can use exceptions in this way and get the proper stack unwinding mechanism, and you can avoid the triangle of doom when undoing. So those are the big guns that you need. If you need partial undos, or if you want partial undos, and you don't want to crash the entire program, then you should try to avoid the triangle of doom and use a non-standard control flow mechanism. So you should use goto in that case. The argument that you need to persuade everyone around you about is that what happens if the program crashes when undoing, or is it appropriate to even try to undo if the program can crash in the middle of doing something in such a way that you can't undo it anyway? Because if you're crashing in the middle of doing something or crashing in the middle of undoing something, then you're not able to completely undo it. So is this even worth doing? Maybe not, but if it is worth doing, it is at least worth doing correctly. And this, with scope exits and scope failures, this is the correct way to do it. So, conclusion for today. Traditional error handling, it doesn't actually handle errors. Error returns, they just return errors, they don't do anything. It's just a value. Values don't do anything. In order to handle errors, you actually have to try again. This means either full restart or a partial redo. Error detection can fail at detecting errors, so you want to detect success instead. If you're detecting success instead of looking for failures, what you're doing is called an acceptance test. And the best way to handle a crash is with restart, because, well, what are your options? You can't just let it stay dead forever, you need to try again. And if you are able to handle crashes with either process pairs or supervisors, then you're able to handle basically any error, because you can merge any error into pretend like it crashed because we actively crashed it. And then you are able to handle it with the automatic restarting mechanism and you're already back up and running. Optionally to this, you can add some checkpoints to save your progress, but there's again a perfectly reasonable argument to make that the checkpoint might be corrupt, so don't do that because what's the point of a possibly corrupt checkpoint? So there are some necessary things. That is the acceptance test, necessary. Crashing or handling crashing, necessary. Optional things, partial undos. Another optional thing, saving progress. So, that's it for today. Any questions? I will mention some administrative stuff, some small stuff, just to make sure everybody is clear about this. This week, the milestone is to do exercise 3, which is process pairs and some brainstorming on the project. If you haven't finished exercise 2 yet, that's not a problem. It's a milestone, it's not a deadline. Nothing breaks if you aren't able to hit it. And then the milestone for the week after that is to start programming on the project itself by running a single elevator in a new programming language. And there is frankly it's not reasonable of me to expect you to be able to translate the single elevator algorithm in a 4-hour lab session. I don't expect that. The goal is to get started. So keep the projects in your field of view, in your attention, and think about it. Think about the exercises in terms of that. And if you fall behind, you're not actually behind. It's just the goal is to make you spend all 4 hours on every lab session and not feel like we're done for this week, and then you get more stuff to do later on because the amount of stuff that you need to do doesn't change. So that's just to kind of keep that in mind. But yeah, any questions to today's material or future material or project or administrative stuff or literally anything? Yes?
Was kind of the conclusion that unless we're using D or C++11, GoTo is kind of the ideal way?
Unless you're using what, then GoTo is the ideal way?
Unless you're using D or
C++. If you don't have a way to do a scope failure statement in some way, and you're not able to hack it out of something useful, then the GoTo statement is your next best bet. Yeah. But that is, of course, if you have opted for doing a partial undo. If you're like, screw it, I'm not doing partial undos, I'm just crashing the entire thing and restarting everything, then of course you don't need any of this control flow madness. Your control flow then becomes exit. And that's not very much control flow, is it?
You could have pairs of functions pointers and a general procedure saying, do these for me, and then internally, in the module, you have a stack of undo function pointers. And then you can build on top of this with C macros.
Yes. But instead of taking the functions pointers, instead of passing the function pointers yourself, you could grab the function pointers off the stack. Now this is pod racing, right? So, yeah, but yeah, you could do that. And guess what the scope exit macro in C++11 does? It does that, but it grabs the function pointers off the stack. So, fun times. Now, if we don't have any more, then we're going to click stop.